All right, so as I mentioned on last Friday, I believe, we have an in-class assignment problem to work today, and then the rest of our class meeting will be dedicated to reviewing for your upcoming exam. Wednesday is also a fully dedicated review day. So if you have any questions today, that's wonderful. If you don't, think of some questions before Wednesday so we can go over some stuff. All right, so this is the first problem that I have specifically given you guys. There may be one in the homework assignments, I don't remember, where we have multiple energy storage elements. So before we even begin looking at this problem in particular, we are going to sort out if there's any way to simplify things a little bit here. So in order to make that happen, I'm going to identify my nodes. So I have this node up here in the top left. With my switch open, I have this node right here. And also this node over here. I've got a node right here. And then lastly, I have this node down here. So to me, it looks like we have 5 nodes in total. And the thing that I'm the most interested in doing right now is figuring out if I can combine those two inductances into a single inductance. So based on how I have identified my nodes, do we think that those inductors are connected in series, they're connected in parallel, or they aren't connected in either of those configurations?
It appears to be parallel.
In parallel. So both inductors are between the purple node in the middle and the green node wrapping around the bottom to the right. So what would 3 Henrys in parallel with 1 Henry look like?
Be 3 times 1 over 3 plus 1.
All right, so 3 times 1 over 4 to me looks like 750 millihenries, or let's just call it 0.75 henries. All right, so we're going to replace those two inductances with a single 0.75 Henry inductance, and we just need to make sure that effectively that equivalent inductance shows up between what I have labeled as my purple node and what I have labeled as my green node. So other than that small change there, we should be attack the circuit kind of as is, just using our basic process that we've done before. So I'm going to start by analyzing the circuit at t is equal to 0 minus. And at t is equal to 0 minus, our circuit should look something like this. So we've got our 10-volt source like so. Here's our 4 ohm resistor. We have an open circuit up top because the switch has been open for a long time before closing at t is equal to 0. Here we have a 5 amp source, and we're interested in finding the voltage drop across the current source at 0 minus. We've got a 4 ohm resistor. We've got a 6 ohm resistor here. A 12 ohm resistor here. And then I'm going to continue to draw this line down here, and we're going to sort a couple of things out. So what I'm going to do here, and this is mainly to help explain why I'm putting the equivalent inductance where I'm putting it, I'm going to label my nodes with the exact same colors that I did above. So if I'm not mistaken, I had a red node up here. Let me scroll up. A green node along the bottom. I had an orange node around here. Blue node on the top right. And then a purple node here. So my equivalent inductance was between my purple node and my green node because my inductors are both between the purple node and the green node. So as long as I place my inductance between those two nodes, I'm good to go. Well, at DC, we know that our inductance should be a short circuit. So I'm just going to put a short connecting my purple node to my green node. And then while I'm at it, I'm going to go ahead and continue that on like so and like so. And this, because those two nodes are connected by shorts, by a short circuit, it means that it should be the same node. So this is my what my circuit should look like at t is equal to 0 minus. And even though we aren't specifically asked for it, I'm going to make a point to find my inductor current at t is equal to 0 minus, because we need to know that piece of information to figure out what's going on at t is equal to 0 plus. So before we analyze this, does anybody have any questions, comments, or concerns about how I've redrawn our circuit? All right, so how might we go about solving for either VCS at 0 minus or IL at 0 minus? Or are there any observations that we can make that would make our analysis a little better?
Well, we know that the resistors 6 and 12 are not going to have any current.
Exactly right, Austin. So the 6 ohm resistor and the 12 ohm resistor are effectively shorted out because that combination is in parallel with our inductance. So this guy right here and this guy right here will not contribute anything at all. So we can treat them as if they were open circuits effectively. So to me, that makes things significantly easier to look at, in as much as we really only have one unknown voltage in this system. So the voltage at the orange node, if we were to consider the bottommost node or the green node ground, then the voltage at the orange node with respect to ground is the current source voltage that we're interested in. So that's kind of how I'm going to play that, right? So I'm going to label this bottommost node as ground. I'm going to call this nodal voltage V1, where V1 is the exact same thing as VCS. And if I can solve for that, that should actually give me enough information to get both VCS at 0 minus as well as IL at 0 minus. So applying KCL at node 1, I'm going to have V1 minus 10 volts over 4 ohms minus 5 amps plus V1 over 4 ohms is equal to 0. So just to be clear, the first term is the current flowing up. The second term is the current flowing down. And the third term is the current flowing to the right. So anybody have any questions, comments, or concerns about how I've applied Kirchhoff's current law at node number 1? All right, so I can now solve that simple one equation, one unknown system, as it were, using the numerical solver on my calculator. So I'm going to put in x minus 10 over 4 minus 5 plus x over 4 is equal to 0. And solving that gives me V1 is equal to, calculator's thinking, 15 volts. So from that, we know that VCS at 0 minus is just V1 minus 0. So that's 15 volts. And we could also hopefully see that our inductor current IL at 0 minus is V1 over 4 ohms. So that's 15 volts over 4 ohms. So we'll just call it 15/4 of an amp. Does anybody have any questions about our analysis there?
Would we be able to use current division to analyze the current over the right-hand side 4 ohm resistor?
Yes and no. So what I mean by that very specifically is if we were doing superposition, yes, but because there is a 10-volt source on the left-hand side, we don't have the current source is not directly in parallel with this 4 ohm resistor because of the 10-volt source. So if we were to do superposition, we know that, like, effectively, just as a quick heads up, right? So doing superposition with this one on and this one off, we know that half of the current is going to split off, right? So that would be 2.5 amps is the contribution from the 5 amp source. And then if we had this voltage source on and this voltage current source off, we could say that we would have 10 volts over 8 ohms. So 10 over 8 is 5/4, which would be 1.25 amps from the 10-volt source. Adding those together, we get 3.75 amps total as our current IL naught, which is the exact same thing as 15 over 4. So superposition would have been a reasonably good way to get at least that inductor current as well. But I don't use that unless I really have to. Did I answer your question, Austin?
Yes, thank you.
No problem. Any other questions about this part before we move on to step number 2? All right, so let me add another sheet here. So for step 2, we're going to analyze the circuit at t is equal to 0 plus. Okay. So at t is equal to 0 plus, our switch is closed. So our circuit should look something like this. We've got our 10-volt source here, 4 ohm resistor across the top. Here's VCS at 0 plus, 4 ohm resistor here. Where our switch was is now a short circuit. Here's a 6 ohm resistor. Here is our 12 ohm resistor. What should our inductance look like at t is equal to 0 plus?
Is it a current source?
It is indeed a current source. And the direction of the current source should be the same direction as IL at 0 minus. And the value of the current source should be the same value as IL at 0 minus. So if I'm not mistaken, that was 15/4 of an amp, like so. Let me make that a little more legible. Okay. So, do you guys have any thoughts on how we might analyze this particular circuit to find VCS at 0 plus?
To start, the 4 and 6 ohm resistors are in parallel.
So the 4 ohm resistor and the 6 ohm resistor are most definitely in parallel. We can see that rather easily for if some of you can't by simply identifying all of our nodes. Another reason that I have chosen to identify all my nodes here is to give myself a quick count, right? So I can see pretty easily here that there are 4 nodes, one of which will be ground, which means I would have a 3 equation, 3 unknown system using nodal analysis. If I were to use mesh analysis, I would have 4 meshes. So that would potentially be a 4 equation, 4 unknown system. So I'm going to choose to do nodal analysis in order to solve for that voltage VCS at 0 plus. So let's just label this one as V1 again, then V2. We'll put this one as ground, and we know that the nodal voltage here is simply 10 volts with ground at the bottom node. So we really only have a 2 equation, 2 unknown system to deal with. So KCL at node 1 is going to give us V1 minus 10 volts over 4 ohms plus V1 minus V2 over 4 ohms plus V1 minus V2 over 6 ohms plus V1 over 12 ohms is equal to 0. So just to be clear, that's this current plus this current plus this current plus this current added together. So there are 4 different, oh, looks like I missed this guy right here. Minus 5 amps is equal to 0. So there are 5 different paths branching off of V1, so that's why our node 1, so that's why I have 5 terms, and I apologize for missing the current source there. KCL at node 2, I'm going to be adding this current, and this current together. So that's going to look like V2 minus V1 over 4 ohms plus V2 minus V1 over 6 ohms plus 15/4 of an amp is equal to 0. And solving this system, I will get V1 and V2. So let me do that really quickly. So I have a 2x2 system. My coefficient for V1 in my first equation is 1/4 plus 1/4 plus 1/6 plus 1/12. My coefficient for V2 is negative 1/4 minus 1/6. And my constant term is going to be 10/4 plus 5. In my second equation, my coefficient for V1 is negative 1/4 minus 1/6. My coefficient for V2 is positive 1/4 plus 1/6. So 4 plus 1/6. And my constant term should be negative 15/4. And in solving that system, I get 45/4 of a volt and 9/4 of a volt. And by inspection, we can see that 45/4 of a volt is also the value for VCS at 0 plus. Does anybody have any questions or comments about our analysis at t is equal to 0 plus? Alrighty, so we'll now analyze our circuit at t is equal to infinity. So at t is equal to infinity, our switch is closed and our equivalent inductance looks like a short circuit. So that gives us the following circuit to analyze. Here is VCS at infinity. So I think that once again, nodal analysis is probably going to be the easiest way to do this because I believe I only have really just the one node where I don't know what the voltage is. Let me double check that. So there's one node. There's that node. And there's that node like so. Yep. So let's call this V1, make the bottom node ground. And we're going to be adding together the following currents. So this one, this one, this one, this one, and this one. So that's going to look like V1 minus 10 volts over 4 ohms plus V1 over 4 ohms plus V1 over 6 ohms plus V1 over 12 ohms minus 5 amps is equal to 0. Solving this for V1. So let's see. That's the same. Six. Just waiting on my calculator to decide to come up with an answer. Here we go. I get 10 volts, and that is the value for VCS at infinity as well. Anybody have any questions or anything about my analysis at t is equal to infinity? Okay. Step number 4 is going to be to find tau during the transient. So way back at the very beginning of the problem, we found out that LEQ was 0.75 henries. So we already have that part done. To find, sorry, go ahead.
Dr. Hartman,
Yes.
do we not need the current there on that one we just got done with?
So if we scroll up to the very beginning, we are asked to determine VCS as a function of time. So we don't really need to know what the current is doing at infinity because we're not trying to solve for the current in particular, if that makes sense. Like realistically, the only point in time that we really need to solve for the current is at 0 minus, so that we know what's going on with the inductor current at 0 plus. At infinity, because we weren't asked for it, we don't need it. Does that make sense?
Yeah, that makes sense. Thank you.
All right, so finding our equivalent resistance. So I'm going to draw my circuit out. And this open circuited set of terminals here is where I've taken my inductor out. So those are the terminals that I'm looking into. I need to make sure that I'm looking at a dead network, which means I need to turn off this current source, as well as turn off this voltage source. So I'm looking into here to find REQ. So once again, just to make sure I don't make any mistakes here, I'm going to wind up identifying my nodes. So I've got this node here. I've got a node here. And then I've also got a node here. So I'm going to label this one A, this one B, and the red node C. So between A and C, so there's no way for me to go directly from from A to B. My apologies there. So I'm going to have to go through that intermediate step of going to node C. For me to go from A to C, I have the option of either the 4 ohm path, this guy right here, or this 6 ohm path, which means this looks like 4 ohms in parallel with 6 ohms. And then to go from C to B, I have the option of going through either this 4 ohm path or this 12 ohm path. So that means I have 4 ohms in parallel with 12 ohms over here. So that looks to me like, let's see, 4 times 6 is 24 over 10, so 2.4. And then 4 times 12 is 48 over 16. So REQ is 5.4 ohms. From this, tau is 0.75 henries over 5.4 ohms. Gives me 0.138 repeating seconds. And then the inverse of tau is 36 fifths per second. Anybody have any questions about finding REQ or calculating tau? Alrighty. So lastly, we'll sneak this in right down here. Step number 5 is simply to plug stuff in to our generic equation. So VCS as a function of time is going to be, so what was VCS at 0 minus? Well, if we scroll up here, I believe it was 15 volts. It was indeed. So we're going to have 15 for t less than 0 minus. Then we're going to have 45 fourths minus 10. So that is 5 fourths. E to the negative 36 fifths t plus 10 volts for t greater than or equal to 0 plus. All right, so that is the in-class assignment problem for today. So what do you guys want to talk about now? There any questions from any of the practice exams that are bothering you guys, or any homework problems or anything?
Oh, I'm sorry, Dr. Hartman. I was muted.
No problem. And also, so Caleb just asked if we could do question 20 on test 2020 from the fall. So I'll do that one first, and then I'll answer your question. Austin? So let me find that question really quickly from that old exam. Tests. Fall 2020. Question 20. Okay. So in this particular question, we are given the following circuit. So we have a time varying voltage source, Vs of t, that is connected in parallel to a 23 millifarad capacitance. And that is in parallel with a 47 millihenry inductance. The current Is of t is flowing out of the positive polarity terminal of the voltage source. The current IC of t is flowing down through our capacitor, and the current IL of t is flowing down through our inductor. We are given the following information. The source voltage Vs of t is 68 times e to the negative 52t millivolts, and IS at 0 is 32 milliamps. And in question 20, we are asked to find IL at 8.4 milliseconds. All right. So this is very similar to homework 12 problem 5. We have a circuit that contains 3 elements that are connected in parallel, which means I'm going to use Kirchhoff's current law here. So Kirchhoff's current law tells me that IS of t is equal to IC of t plus IL of t. We're going to use that piece of information in a moment. We can also say that IC of t is going to be C times the derivative of our source voltage with respect to time. And furthermore, we can say that IL of t is going to be 1 over L times the integral from some point in time t naught to some later point in time t of Vs of t prime dt prime plus IL at t naught. Okay. So our ultimate goal for part 20, or for problem 20, is to find IL at 8.4 milliseconds. So this is the one that I'm going to focus most of my attention on. Okay. So IL of t in general will be, so I'm going to have 47 times 10 to the minus 3. So that gets rid of my milli. A Henry is an volt second per amp. So there's my 1 over L term. Now I'm going to be integrating from 0 to 0.0084 seconds for my voltage waveform, which is 68 times 10 to the minus 3 volts times e to the negative 52 t prime dt prime plus whatever IL at t naught is, which we don't know that yet. So let's do a couple of things here, right? I can see that this volt here cancels this volt here, and this 10 to the minus 3 here should cancel this 10 to the minus 3 here. So what I'm looking at is 68 over 47. And I have an amp in the numerator and seconds in the denominator. How do I take the integral of e to the negative 52t?
Be 1 over alpha e to the alpha t.
Yep, so that's going to look like 1 over negative 52, and the units on that 52 should be per second. And then I'm going to have e to the negative 52t prime evaluated at 0.0084 seconds and 0 here, plus IL at T naught. So now we can observe that this second and this per second cancel each other out. I'm going to do a little bit of math here. So let's see. 68 over 47 times -1 over 52 looks like -17 over 611 amps. E to the -52 times 0.0084 is 0.64610 and some change, minus e to the 0, which is just 1, plus IL at T naught. And then all of this stuff on the left-hand side is literally just a number. So let's see. So -1 times -17 over 611. So that looks to me like positive 0.0098466 and some change amps plus IL of T naught. And I'm just going to call this 9.847 milliamps plus whatever IL at T naught is. So we have done the bulk of the heavy lifting here. The last thing we really need to figure out is what IL at T naught is. And we're going to do this the exact same way that we did it when we worked homework 12, problem 5. So doing a little bit of finagling with our KCL expression, I could say that IL at 0 is equal to IS at 0 minus IC at 0. And now if we play around with our relationship for IC, so we have 23 millifarads, so that's 23 times 10 to the minus 3 amp seconds per volt times the derivative of our voltage expression. So that's going to pull down a -52 per seconds, a 68 times 10 to the minus 3 volts, E to the -52 times 0. So that means that this part right here just goes to 1. If I look at my units, I have seconds being multiplied by per seconds. I have volts over volts. So everything's going to come out to be in amps now. So 23 times 10 to the minus 3, -52, 68 times 10 to the minus 3. So that comes out to be -0.081328 amps, or -81.328 milliamps. So that's going to be 32 milliamps, -81.328 milliamps. And I'll put this up here. So let's see, times 1,000. 113.328 milliamps is IL. So 9.847 milliamps plus 113.328 milliamps gives me 123.175 milliamps. By the way, and I'm only mentioning this because I had a student come to my office earlier, your calculator can actually do the overwhelming majority of all the calculus that I just did by hand there. So that would save you a considerable amount of time. All right, Austin, what was your question?
I asked what if the complexity was comparable to these old exams, and that was about it.
Oh, absolutely.
I'm doing a lot better since our conversation the other day.
So I will reiterate. I believe that the practice exams that I've given you, as well as the in-class assignments, are a very good way to study for this upcoming test or any tests in my class, because those are questions that I wrote in particular. Just to reiterate, the material for exam 2 is just Thevenin and Norton equivalent circuits, both with and without dependent sources. So I do expect you to be able to know how to use the test source method to find Thevenin resistance directly on at least one problem. Then we have capacitance and inductance problems. And then we have transient analysis. That is all the material that's on this upcoming test. So it's really just 3 broad topics as opposed to like 8 smaller ones. So I think it should be easier because there's less stuff to have to know how to do. And for what it's worth, problem 19 and 20 from fall 2020, so the one effectively that I just worked, would be the absolute hardest thing you should expect on the test. And it's literally a homework problem that you guys were asked to do. What else can I help you all with today?
When going through the transient problems for studying, would you say that just setting up each step would be a good way to kind of learn how to do that?
Yeah, so there is something that potentially trips folks up every now and then on the transient problems. I'm going to see if I can find one on the test really quickly. There isn't one on the fall test. Let me see if I did on the summer. I don't think I have one of these old tests because I was allowed to make it long enough. So something that I've been doing here recently, I've been trying to make it to where there's 4 questions associated with an RL circuit and there's 4 questions associated with an RC circuit. Now, there are 5 steps when we have a total response problem. So one thing that I have been doing is the first question for the total response problem might be to, it might say to find the capacitor voltage at T is equal to 0, or to find the inductor current at T is equal to 0. And then we move on to directly to what's going on at T is equal to infinity in the next problem. So that may seem like a little bit of a curveball there, but I want you guys to remember that since the capacitor voltage cannot change abruptly between T is equal to 0 minus and T is equal to 0 plus, and the inductor current can't change abruptly between T is equal to 0 minus and T is equal to 0 plus. Even though it doesn't say analyze it at 0 minus, that's exactly what you're supposed to do. I hope that made sense. I can put a quick, like I can draw a simple circuit to kind of explain what's going on or what I meant by that. So let's say that we had the following circuit. So the first part of this problem, which I'll just call it A, would be to say find VC of t at t is equal to 0. Then B would be find VC of t at t is equal to infinity. C would be find tau. And D would be find VC at t equals, let's just say 1 millisecond or something like that. Like the reason why I've skipped the analyze the circuit at t is equal to 0 plus step is because this voltage can't change between 0 minus and 0 plus. So whatever you find at 0 minus is the answer for 0 plus as well. If you've looked at the practice tests and all of that kind of stuff, I have the various steps or the parts of the problem are broken up into the exact steps that I've been asking you to do. So it's analyze the circuit at 0 minus, 0 plus where appropriate, infinity, find the time constant, and then figure out what's going on at some specific point in time. So all of the example problems that we've been working, homework problems, all that kind of good stuff are very good practice. So as long as you're putting the steps into practice correctly and then do whatever analysis is required to determine your quantities, then you're good to go.
Thank you.
No problem. I hope I didn't rant too long about that.
No, that helped.
What's next?
I mean, I don't really have a question, but could we just work that one out since it's right there already?
Absolutely.
Sweet.
So, so here's our analysis for part A, right? So at part A, our switch is opened. So we're going to have our 10-volt source like so. Here's our 12-ohm resistor. Our capacitor is going to look like an open circuit. Let me give myself a little bit more room so I can put my polarities for my voltage. Here is our 1 amp source. Okay. So ultimately, we're trying to find VC at 0 minus here, and that's the only thing that we're interested in, with positive polarity on the left and negative polarity on the right. So before I do anything here. Do any of you guys have any thoughts on what we might need to do? All right, so I will ask a question then. How much current is flowing through the 12 ohm resistor?
Hmm,
Should be none.
It is none because the 12 ohm resistor is not part of a closed current carrying path. So that means I have 0 amps across it, and therefore I have 0 volts. There's going to be 0 amps flowing through it and 0 volts across it. So why I have decided to notice that in particular is because that means that the positive polarity terminal of this capacitor voltage could be at this bottom node down here because there's no voltage drop across the 12 volt source. So really, the voltage drop across the capacitor is just the voltage drop across the 3 ohm resistor, positive polarity on the bottom. So how would I solve for that?
Ohm's law?
Ohm's law, absolutely. So VC at 0 minus is just going to be 1 amp times 3 ohms. And then I need a negative sign out front because the current is flowing into the negative polarity terminal. So that looks like negative 3 volts. Okay. Now, for what it's worth, you could have gotten the same result by effectively doing nodal analysis, right? So if you put a voltage V1 here and a voltage V2 here and called your bottommost node ground, when you apply KCL at node 1, you'll literally have V1 over 12 is equal to 0, which lets you know that the voltage drop across that 12 ohm resistor is 0 volts if you didn't observe it the way that I did. So there's definitely a different way to do it to get the same result. That's since what I did might not be obvious to all of you. Any questions about this part before we move on to the second part? All right. So for our second part of the problem, we're just jumping straight ahead to t at infinity because we know that VC at 0 plus has to be equal to VC at 0 minus. So at infinity, our switch is closed. So we're going to have our 10 volt source like so in parallel with our 12 ohm resistor. So how might we figure out this capacitor voltage at infinity?
I mean, I would probably do nodal, but you probably could do something easier.
You could indeed. So what's the voltage drop across the 3 ohm resistor positive polarity on top?
3 volts.
So now we could just do KVL around this path and find out that VC at infinity is 10 minus 3 is 7 volts. It's effectively the same thing as doing nodal analysis to find that the voltage, nodal voltage here is 10 volts, the nodal voltage here is 3 volts, and then 10 minus 3 is 7. Same thing, just a different perspective. Any questions on my analysis for part B? Alrighty. So part C, we're trying to find our time constant. So I'm just going to go ahead and draw this with my voltage source turned off. And my current source turned off. So what's REQ?
15.
I disagree.
Three.
3. The 12 ohm resistor is shorted out because it's in parallel with this short circuit over here, so it's not going to contribute. So the only resistance our capacitor sees during the transient condition is the 3 ohm resistor. Our equivalent capacitance, if I'm remembering correctly from up here, is half a farad. Yep. Which means tau is 3 times 1/2, or 3/2 of a second, and the reciprocal of tau is then 2/3 per second. And then lastly, for part D, we know that VC as a function of time would be -3 volts for t less than 0 minus. And so then it's going to be -3 minus 7. So that would be -10 e to the -2/3 t plus 7 volts for t greater than or equal to 0 plus, and we would simply plug in t is equal to 1 millisecond or whatever into that expression. Any questions?
So Dr. Hartman, it's a little bit of a nuance, but when you calculate tau, the general equation that we got for example, an RC circuit would be, it'd be e to the negative t over RC.
Mm-hmm.
Can we just do negative t over RC instead of doing the tau and then finding tau inverse?
Sure. It's the same thing.
I didn't know if that would like if
Yeah.
that became an issue on some problem, maybe where you're given some value in tau and you have to use the inverse.
No, so tau is just for an RC circuit is literally R times C. So the generic expression, let me just put it down here. Y of t would be y at 0 minus for t less than 0 minus, and then y at 0 plus minus y at infinity for e to the negative t divided by tau plus y at infinity. So it really doesn't matter if you replace this t with RC or not, you're doing the same thing.
Yes, sir.
Yep, so tau is equal to RC for RC circuits, and tau is equal to L over R for RL circuits. It's all the same thing. And that looks too much like RC. There we go. I'm now trying to sort out if I could give you tau and make you work backwards to find the value of the energy storage element, but I don't think I would be that mean.
No, sir, you didn't hear anything.
Yeah. I don't think I'll be that mean for this summer's test, but that sounds like something That sounds like a douchebag move I would pull later on, so maybe, but not for you guys. Don't worry about it.
That never came out of my mouth.
Yep. What's next? All right. Well, I hope you guys have a great rest of your afternoon. If you have any questions about anything, feel free to email me. I'll be working on your exam for the next day and a half or so. And I'll see you guys on Wednesday afternoon for further review. So come with plenty of questions. Have a great rest of your day.